Hi, my name is Rubén Heradio, and I work at the Spanish National University based on distance learning, UNED for short. I'm going to present some work we are doing in collaboration with researchers from the University of Seville. Imagine I'd like to buy a new car, so I visit the webpage of the car manufacturer, and then in the configurator, I select the model I'm interested in, which is called Spring. The configurator asks me to choose between two possible versions, expression and stream. Imagine that I select expression. Then the configurator asks me to select the powertrain, which can be electric 45 and electric 65. And if I select electric 45, the configurator asks me to select the color of the car, and it gives me four possibilities. Imagine now that I change my mind, and instead of expression, I select the other version, the extreme version. Then, as a result, the configurator prevents me from selecting the electric 45 powertrain, and who knows why, it also limits the number of available colors to just two colors. Internally, the configurator is managing something called a variability model. A variability model is a specification of the configurable features and their interrelationships. In this example, we have three choices. The first choice to select the version of the car, the second to select the powertrain, and the third choice to select the color of the car. Inside every choice, we have different alternatives, which are Boolean in the sense that they can be enabled or disabled. And in this particular case, there are some features that have some dependencies. For instance, here you can see that electric 45 depends on expression, which means that to select electric 45, to enable that in a configuration, we need to enable expression as well. Okay, let's move on the topic of this talk, which is software. So there are some software systems which are highly configurable. For instance, you can see here an excerpt from the variability model of a system called Corvus. In this variability model, there are two optional features here, and there are also two choices. The first choice has four alternatives, and the second one has two alternatives. There are also some dependencies between features, so basically the same story than in the example before. I dare you to answer this question. Does feature no GFX in it depend on any other feature? In other words, in every configuration where no GFX is enabled, are there any other features that also need to be enabled? To answer the question, start looking at this dependency here. So please stop the video, try to solve the problem, and then start again. Welcome back. Let's work the solution step by step. First, HaveVGA text frame buffer depends on not selecting no GFX in it. In other words, the first feature excludes the second one. As you can see here in this logical proof, exclude relationships are symmetrical, which means that this is totally equivalent to saying that no GFX in it excludes HaveVGA text frame buffer. But this other feature depends on this one. As this is disabled, this also needs to be disabled. And we are in a choice of only two alternatives. So as this is disabled, this other alternative needs to be enabled. But this alternative to be enabled needs that this feature is also enabled because it depends on it. So the answer to the question is yes. No GFX init depends on other two features, which are BVE linear frame buffer and HaveVBE linear frame buffer. The moral of the story is that in variability models, we specify direct relationships between features. But as we start chaining those direct relationships, many more indirect or transitive relationships arise, and dealing with those indirect relationships is extremely hard. This example has 8 features, but the whole model of Corvus has more than 3,000 features. And in the literature, there are variability models even more complex. For instance, this version of the Linux kernel has more than 18,000 features. What do we propose to deal with all those indirect relationships? Well, what we propose is to make explicit the most important one, which are strong dependencies and strong conflicts. Here, with strong, I mean relationships that are held in every configuration of the variability model. So the basic idea is that from a variability model, we are going to extract automatically all strong dependencies and all strong conflicts, and we are going to model them as graphs. For instance, here we have a dependency graph, which is a directed graph. You can see arrows where each node accounts for a configurable feature and where each arrow accounts for a direct or indirect dependency. Okay. For instance, we saw in the example that no GFX init depended on this feature and on this other feature. So you can see here the arrow. I've used different colors to highlight the connected components of the graph. And an interesting concept here is the degree of the nodes. In a directed graph, we have in and out degrees. The in degree is the number of incoming arrows into a node, and the out degree is the number of arrows that come out of the nodes. For instance, the out degree of no GFX init is 2. There are 2 arrows that go outside this node, but the in degree is 0. But here, BBE linear frame buffer has an in degree of 1 and an out degree of 1 also. The conflict graph is similar, but as the exclude relationships are symmetrical, there are no arrows. And also, we don't make a difference between in degree and out degree. We here only have degree. Also, I should mention that there are 2 extreme cases, which are core and dead features. A core feature is a feature that needs to be enabled in every configuration, and a dead feature is a feature that has to be disabled in every configuration. So these features are not represented in the graphs, but are given in 2 lists. Once we have the graphs, we can use the machinery of network analysis tools such as Pajek, Gephi, or iGraph to examine the role of particular features. For instance, in this version of the Linux kernel, we could look for the in degrees and find that the most reused feature is this one, okay? And also using computing the adjacent nodes to this feature, we can identify the features that depend on this very reused feature. So this can be helpful, for instance, to spot features that if are changed, the modification can be easily propagated throughout the whole system. Or, for instance, if we want to improve the performance of the energy consumption of most configuration, a good place to start is with this kind of features, very reused. And the same with the most conflicted, the most incompatible features, which can be easily detected in the conflict graphs. Even more, we can go beyond analyzing particular features and analyze the whole system. For instance, in this version of the kernel, 20% of the features are dead. This means that almost 20% of the features should be removed from the system. Also, we can represent an histogram of the node in degree distribution in the dependency graph. For instance, in our example, we can see that very few features are highly required by others, whereas most features are hardly required by others. These patterns indicate that the system is robust to changes in random features. In other words, if we make a random change, the probability of doing it here is very low because there are only a very few features. Probably the change is going to fall here. And as the degree of these features is very low, yeah, this change is not going to be propagated. Also, we can represent a scatter plot of the nodes in degree versus their out degree. Here, every point represents a feature, and its x and y axis account for its in degree and out degree. So if we look at this green area, we can see that highly required features have few dependencies. Okay, that is, the features with a high in degree tend to have a very low out degree. And this is again good news, because if we were here in this red area, those features would be very sensitive to changes to other features because they would have high out degree, and their potential modification would propagate to many others because they would have very high in degree. We can do the same with the conflict graph. For example, here you can see the histogram representing the distribution of the node degree in the conflict graph. And in this histogram, you can see that most features, most nodes are compatible with others, whereas only very few features are highly incompatible with others. So if we remove the dead features, the incompatibility problem is basically solved. Well, how does our magic works? I'm not going into the details, but basically we have developed a tool which takes a simple the variability model, it translates it into a Boolean formula, and using such technology, it extracts the graphs and the list of depth and core features. Using this tool, we have generated a dataset with the graphs of almost 6,000 variability models. This dataset is diverse in terms of domain. Most of the systems come from the system software domain, but we also have systems from security, finance, automotive, etc. And also the dataset is diverse in terms of their complexity. So you can see here the histogram of the distribution of the number of nodes, the graphs, and also the distribution of the required arcs in the dependency graphs, and the distribution of the exclude edges in the conflict graph. To give you an idea of how complex is the largest model, we have a model with almost 36,000 nodes, which has more than 6 million required arcs in the dependency graph, and whose conflict graph has more than 4 million exclude edges. Our tool and our dataset is freely available at this open repository. Thank you so much. I'm open to any question, advice, or offer for collaborating. Bye.